Hi, Birdbound. Welcome to Math Analysis Day 4. Today we're talking about matrices. Matrices have many important uses. One of the simplest is to store data. In fact, most common use outside mathematics is to store data. Matrices are also used to solve linear systems, represent geometric figures and transformations. Building on this geometric interpretation, matrices can also be used in the study of trigonometry. So, for example, you may have a matrix that is 1, 3, 0, 2, 4, negative 1. That's a 2 by 3 matrix, which means you have 2 rows by 3 columns. Or you could have 6, negative 5, 0, 1. That's a 1 by 4 matrix, where you simply have 1 row and 4 columns. It's a list of data. You can do operations with matrices, meaning you can add them and you can subtract them. But notice that the orders have to be exact, meaning they have to be literally the same dimensions in order to add or subtract. Rules for matrices. If P and Q are two matrices of the same order, then the sum of P and Q, denoted by P plus Q, is a matrix with its elements being the sum of the corresponding. If P, the difference of P and Q is denoted by P minus Q. If they're of different orders, then their sum or difference is not defined. So here in this example, I cannot add those, I can't subtract them, I can't do anything to them because the orders of them are different. So looking at some examples of multiplying matrices by a real number. So in the top, A is equal to 4, 3, negative 2, 10. If I want to multiply, if B is 2 times A, then I'm going to take 2 times everything in A so that B, my new matrix, is 8, 6, negative 4, 20. Similarly, if I want D to be 2/3 of C, I multiply every term in C by 2/3, and I do get 2/3, 4, negative 2, and negative 10/3. Square matrices has the same number of rows as it does columns, 2 by 2 and 3 by 3, and a zero matrix or a null matrix denoted by O has every element is a 0, and it may be of any order. So, matrix multiplication was invented in the 19th century and is a useful way of combining two suitable matrices. It multiplies elements in a row with elements in a column to produce a single number. To make up some matrix multiplication problems for yourself and to investigate the condition on the sizes of two matrices that is necessary before you can multiply. So, Madeline bought 3 apples, 2 oranges, 4 pears. The cost of each item is 25 cents each, $1.40 respectively. Find the total cost of the purchase. The answer is $4.35. Notice that what we did is we took the 1 row, 3 column matrix of 3, 2, 4 times the 3 row, 1 column matrix of 25, 140, multiply 3 times 25 plus 2 times 100 plus 4 times 40, and you do get 435. Put the decimal place back in, and that is $4.35. A 3 by 3 matrix multiplied by a 3 by 2 matrix will result in a 3 by 2 matrix. A 3 by 2 multiplied by a 2 by 3 will end up with a 3 by 3, and a 3 by 2 multiplied by a 3 by 3 is not possible because, in general, a MN matrix can only be multiplied by an NP matrix to produce an MP matrix, meaning that N has to be the same in both matrices. Commutative and associative properties. In general, matrix multiplication is not commutative. However, it is associative. So I can take A times B, then times C, or B times C, then times A. So elementary row operations and linear systems, If we're going to solve this system, which you will be doing today, our goal is to eliminate the x term from the second equation and the x and y terms from the third equation. And we're going to do that by a system of elimination using nothing but the coefficients of the matrix. So first thing we need to do is identify what our system is and then write our augmented matrix. Notice all I did was take the coefficients across. This is our augmented matrix. Okay. Then this operation right here, I'm going to take row 2 minus row 1, and that will become my new row 2. So 1 minus 1 is 0. 2 minus negative 1 is 3. Negative 2 minus 3 is negative 5. And 10 minus 4 is 6. By doing that, I've eliminated the x term in the second row. Then I'm going to take the third row minus 3 times the first row. So 3 minus 3 times 1 is 0. Negative 1 minus 3 times negative 1 is 2. 5 minus 3 times negative, or negative 3 times, no, 5 times 3, 5 minus 3 times 3 is negative 4. And 14 minus 3 times 4 is 2. By doing that step, I've eliminated the x term in the third equation. If we keep going and take 1/3 or 1/2 of the third row, then all I did was take all of these, 2, negative 4, and 2, and divide them by 2 to get a new third row of 1, negative 2, and 1. Then, in order to get a 0 here, I can take the second row minus 3 times the third row. So 3 minus 3 times 1 is 0. Negative 5 minus 3 times negative 2 is 1. And 6 minus 3 times 1 is 3. Then if we simply switch the second and third rows, which is legal, we have found that z is 3. If z is 3, we can substitute that back in and find that x is 2 and y is 7. So the solution to this system is 2, 7, 3. Thanks for watching.